Okay, ready? We're going to do a problem here using, well, PHYS law. A certain diseased artery has a cross-sectional area that is 70.7% the area of a healthy artery. Compare the pressure gradient in the two arteries if the same volume of blood is to be carried by both arteries per unit time. Okay, so the first thing we notice is we're going to have a healthy versus an unhealthy artery. And they're saying the cross-sectional is different by a ratio of 70.7%. So first thing I might want to write is area healthy is going to be equal to, no, not the area healthy. It's going to be area of the sick one. I'm going to call it sick, S, is going to be equal to 0.707, the area of the healthy one. Okay, that's given. Compare the pressure gradients in the two arteries. Okay, so pressure gradients is this delta P over L. So I'm going to set this up here. We're going to have delta P over L, healthy, is going to be equal to 8 eta Q healthy over pi r to the fourth healthy. Does that make sense? I'm going to assume that the unhealthy blood has the same viscosity as the healthy blood. That makes sense? So I'm not going to put a little h on the viscosity of the blood, okay? That person would be really unhealthy if their blood starts becoming thick or something because of the health problem. Ready? And then we're going to have the gradient of the sick one, length of the sick one, is going to be equal to 8 eta, the volume flow rate of the sick one, over pi r sick to the fourth. Okay? Now, what I like to do is take the ratio, right? And then we can just say this is all equal to, and then what we're going to do, we're going to cancel. And I might not cancel everything, but I'll cancel the more obvious stuff. And we'll rearrange this, and we're going to get Q healthy over Q sick, R healthy to the fourth, R sick to the fourth. Okay? Now, so far, we haven't done anything about this area, okay, being different. Compare the pressure gradients in the two arteries if the same volume of blood is to be carried by both arteries per unit time. Oh, that's telling us that Q healthy is equal to Q sick. So they cancel too. So all we have left is like that. Okay? So how are we going to, this is where you have to realize they gave us the ratio of the areas. So they gave us area sick. What are we going to do? Well, what if we do this? What if we realize that area is equal to pi r to the pi r squared, right? Area is equal to pi r squared. So I could say area sick is equal to pi r 6 squared, right? And well, I can just substitute that in, right? So this equation becomes pi r 6 squared is equal to 0.707 pi r healthy squared. Cancel. And this tells us that R sick squared is equal to 0.7 R healthy squared. Now I could take the square root of that and say R sick is equal to the square root of 0.707. Yeah, I could do that. Or I could realize that in this problem, we're using R to the fourth. So I can square this. I'm going to write this over here. This tells us that R sick to the fourth is equal to 0.707 squared R healthy to the fourth. Right? Now I'm going to plug this in. Let me get, I'm going to get rid of this arrow. 0.707 squared R to the fourth, or R healthy to the fourth. I'm going to just draw a line here to show that this. Okay, so then we can cancel those. And that's equal to, what's 0.707 squared? That's equal to 2. Now, I'm going to write this down because I know that 2. So that's the answer. Okay? The gradient healthy over gradient sick is equal to 2. So the pressure gradient, wait a minute,